Well, the best way to learn vertex sparsifiers is just reading very carefully the thesis of Ankur Moitra. Ankur Moitra in 2011. His thesis at MIT, and his supervisor is Lighton in MIT. So his thesis, the title is Vertex Sparsification and Universal Rounding Algorithm. So we are asked to solve a sequence of optimization problems characterized by cuts or flows so we can compute a good vertex sparsifier, and then we discard the original network. For example, we have a very complex network G, then we want to, and it has some terminals. For example, these are the terminals and other vertices as well. But isn't it nice that we could somehow summarize this graph and create another graph, but this time we have a much simpler network. For example, just we restrict ourselves to the terminals. For example, we could somehow preserve some properties such as congestion or any other graph property. So this is the motivation of thesis of Ankur Moitra. So this guy is very, very genius, and his the way he teaches is very, very nice. He is also a good teacher. So I want to show my own perspective on all stories about vertex sparsifiers and why they are important. I want to say that in partial differential equations, for example, you have Dirichlet boundary condition, which is some function, and then Neumann boundary condition, and also Rabin boundary condition, mixed boundary, Cauchy boundary conditions in PDE, and we want to solve some partial differential equation. For example, this is Laplacian, and on the boundary you wanted to have some constant, and you talk about, theoretical nonlinear PDE. In PDE is about Sobolev spaces. In parallel, in the world of graphs, in networks, we have vertex sparsifiers. And instead of Sobolev spaces, we have cut spaces. These cut spaces. And our boundary condition, these are boundary condition. Our boundary condition here are how to put constraints on something like demand. For example, you have on the boundary condition is that you have a fixed demand. So solve it. Fixed demand. A fixed capacity. So this is why I'm highly motivated, because I can use the analogy and inspiration and the paradigms of PDE to the graphs. Not directly, because this is a continuous world, this is a very discrete world, but you can see how can we use the same analogy in the continuous space to the discrete space. And as you know, the continuous space is like what we do in machine learning, and the discrete space is what we do in combinatorics and computer science. But we can get inspired by going to the other space. And for example, we can have a fixed capacity on certain terminals. Sometimes the solution does not exist and we have to change the capacities, just like here that, for example, some equations don't exist, so we should change our boundary conditions. So we want to run our algorithms on vertex sparsifiers. So I told you that simplified graph is we call it vertex sparsifier. So we can run algorithm on vertex sparsifiers as a proxy and still recover approximately optimal solutions in the original network. And because the network we store in our pocket is very small, we can save space. That's the goal in computer science. And because the algorithm can run a much smaller graph, we can save time. This is another motivation in computer science. So example one that I want to say is we have a graph, as I said, then we have a simplified graph, which is called vertex sparsifier, which has on the same nodes, but now the edges are different. This is another kind of vertex sparsifier. So remember that the vertices are the same. We just changed the edges. And we, for example, our goal is always proving something. For example, expansion in G is greater or is very similar, but greater than expansion in H. Isn't it nice? We have simplified it, put the graph in the pocket, and then we go. So, example 2 is that we have, for example, as long as the integrality gap of a standard LP relaxation is bounded on trees, we can approximate it by tree. I mean, the integrality gap is at most a logarithmic factor larger for general graphs. So for a large graph G, we have integrality gap, which is greater than integrality gap of a tree. So your H is now a tree. Your original graph is G and your tree is H. So we preserve this, but they are almost the same, but a little bit integrality gap for G is greater than integrality. So integrality gap for H we can say is better. So H, we call it H is better. The third example that I want to say is that if you have ever seen the Akamai.com, this website and company, it's a cloud delivery platform, content provider, and they are active in web attack visualization and routing, and they have a small number of data centers distributed throughout some gigantic communication network. And these data stores, we call it terminals, T1, T2, these terminals. So these are data centers. So these are data centers. Of course, we have other computers as well that are not data centers. So these data centers store large files, and they periodically want to transfer some of these files between different data centers. And the goal is finding some routing scheme in the original network that achieves large throughput and transfers the content of these files as quickly as possible. So this was the third example. But the question is there a much smaller communication network that approximates all the relevant communication properties of the original networks? I mean, like the work of David Karger, Bengtsson, and others. So we can reduce the number of edges so that the total number of edges in near linear time is the total number of vertices. And let's call this reduced graph a vertex sparsifier, as I said. So remember, terminals are data centers. So we care about a problem is minimum congestion routing. And you have a demand vector, which, for example, the rate or demand at which we would like to transfer some files or information from data center A to data center B, or demand from going from A to C, demand from B to C, and all of them. So this is a demand vector. And a valid routing solution, it is a choice of flows, one for each pair of terminals A and B. The flow value from A to B is equal to the target rate. For example, let me give you an example. I don't know, it's going like this. It's a kind of bottleneck here. And you get here, for example, to this, like normal things. And so from A to B, we have three different paths. 1, 2, 3. And you see that this edge is very, the congestion is high because it is overloaded. We do not want to overload the bandwidth of the link too much. And so we define the congestion on link E, for example, any link, congestion on any link like E, to be the sum of total flow traversing that link. For example, FE of I from path 1, path 2, path 3, total flow traversing that link. Because each path contributes differently. And divided by the bandwidth, the capacity of that link. So we call it bandwidth of link. And the goal is to find a valid routing scheme, routing solution that minimizes the worst case congestion on any link. So the most congested link in a network is the bottleneck. Bottleneck, and it is something like edge E that is used too much by different paths. For example, by path F1 and path F2. And it's very easy to solve. For example, I highly suggest to read the article of Chandra Chekuri, who is a very nice researcher. The title is the congestion minimization for multipath routing via multi-route flows. So the goal is minimize some congestion, C, this is your congestion, such that the sum of Y of P is equal to K, and also I don't go through the details of this article, but you can solve this relaxation and then round it, and then you get your answer. So it's not a big problem. So it's not very difficult. Of course, always rounding and all those techniques like randomized rounding is very, very interesting and exciting for me. The question is there a graph edge on just a set of terminals so that simultaneously for every demand vector R, the minimum congestion of routing is approximately the same as the minimum congestion of routing in H. So the quality, always talk about quality, because we can have many vertex sparsifiers, but the quality of that vertex sparsifier H is just the multiplicative factor by which H approximates G. Approximates the congestion G, the graph G, as the quality of H. So that's a vertex sparsifier. So the minimum congestion in G congestion in G, we want it to be almost the same as the minimum congestion in H. And the best quality known, it's just this amazing bound. So the order of log K over log K. And you see this in several problems because it's obvious, because everything is kind of natural. You can simplify any question. Many questions, like there's zero extension problem, and the zero extension problem, if you solve it by CKR rounding, then it has this order of complexity. So this is the approximation factor that you get. So I don't know of any improvement better than this. So this is the quality of your sparsifier. So the amortized time to compute a good routing solution is actually independent of the size of the original network and depends polynomially on the number of terminals. A good vertex sparsifier will approximately preserve the value of the sparse cut and the values of a whole list of the NP-hard graph partitioning problems. And so we want our vertex sparsifier H to be such that any demand vector, the minimum congestion of routing it's mostly minimum congestion of routing in G. So minimum congestion subject to, if you have some demands, the minimum congestion should be less than the minimum congestion on G. In fact, we want it to be a sandwich like we do every time. For example, in metric embedding, do you remember? We always want to sandwich and say that it is bounded between lower bound and upper bound. So in H, we choose a target rate R, which is so the bandwidth of link from A to B in H. For example, let me show you an example. Here is A. It goes like this. B. And let's say this is another edge. So we have different paths from A to B. So the flow is divided into like this, for example, like this. F1, F2, F3. So this is a graph G. And your sparsifier could be just A and B. And remember, our terminals are just A and B. And here we have A and B. So isn't it nice that we do such thing? And here is H, and so here is the R, the demand from going from A to B, and it is the bandwidth, and the bandwidth is just the capacity, and so we approximate G by H. So once we have a good H, then the incremental running time to compute a near optimal routing of R and G is just the time to run a minimum congestion routing on H. Because if we solve the minimum congestion on H, then G is with us. So note that the set of demand vectors R that can be routed in G with congestion at most 1 is called the unit congestion polytope. And also a good vertex sparsifier not only approximately preserves the unit congestion polytope, but also the values of combinatorial parameters, such as sparse cut value and etc. And from these things that I said, we can compute a good vertex sparsifiers as you should imagine the sparsifier as a pre-processing step, because when you calculate H with some pre-processing time, then you're done. You're ready to deal with any kind of problem, because instead of focusing on your original problem G, you focus on the smallest and easiest problem H. which you have spent time before for pre-processing, and now we are ready to deal with the problem. And if you want to make H small, and we want to, and sometimes you want to H to be convex combination of contraction-based trees. So a weakening condition is